Okay, so good afternoon, everybody. I will start by thanking Clee for inviting me here. It's always very nice to be under the sun of West Coast. So I'll start. I will be giving this talk, which is some kind of warm-up for what Piero will be talking about later. So it's a warm-up and concerns two important adjectives, which is magic and exceptional, and I will show you how they can fit together. And let me start with with a summary of the talk. I will start by considering the magic star as a unifying tool for exceptional algebras, and I will stress in which sense they are exceptional. So in a sense which is slightly different from the Cartan classification, from the usual thing that exceptional algebras single out because they don't fit in a kind of infinite sequence like the classical ones. So then as a second point, which is related of course to the first, I will introduce the so-called spin factor embeddings, and as you will see also in the next talks in the coming days also, they are crucial in order to make attempts to unify theories in which both bosons and fermions are in the same representation of a symmetry. And then as a third point, as you know, all this can be generalized in an infinite way, of course paying the price of losing some properties which anyhow are good and make sense, for example in the perspective of discrete space-time, in particular of discrete space, which is exceptional periodicity, EP, and related magic star projection beyond the eighth. As a special argument, special topic within EP, I will talk about a certain class of matrix algebras which are not so much known to mathematicians as well to physicists, and they go under the name of Vinberg's T-algebras, are a very clever generalization of Jordan algebras. Next, the issue of triality. Triality has always been a very inspiring topic in many branches of mathematics and of course also of theoretical physics. And I will highlight the emergence of triality in these models and how triality is broken and in which way is broken in exceptional periodicity. I will also mention in passing the strange case of 24 dimensions and the so-called weak triality, which at the moment is just a curiosity, but still there is some work in progress about that. I will conclude on how one can attempt to characterize the algebras that essentially are emerging from exceptional periodicity, which are not Lie algebras. So there are some attempts in trying to characterize these kind of algebras. And of course, as a conclusion, I will mention some developments and work in progress. Okay, so I will start with magic star projection or embedding for exceptional algebras. This was actually found and studied in depth by Piero back in 2012. We were very surprised recently in finding that a very well-known mathematician, Mukai, a Japanese mathematician, actually found this very structure, the structure of the magic star back in '94. Of course, he just glimpsed it, so he just actually considered and, for example, identified the Jordan algebras on the tips of the star, but didn't go farther in depth. But we are pleased that essentially this mathematical structure was already identified essentially some 20 years or something before Piero. Of course, Piero went much more in depth and then applied to some physical problems, and we still are.
Mike was not there to name it magic.
Oh yes, of course, because we all hold the. I mean, the name magic was made by Mike G2 decomposition, because of course G2 actually has this very structure, the roots of G2 projected on the two-dimensional plane spanned by the two roots of his A2 subalgebra have this structure. Of course G2 has nothing in the center, and that's the very reason for which G2 cannot be exceptionally periodized. That's the point.
Alessio, so this star here is a symbol that conveniently creates a pattern where each of the antipodal pairs on the star intersects the point at the centroid of the star, right? So it's a symbol. But if you wanted to have an interesting three-dimensional analog that achieves the same thing, there are...
well, it happens that we just actually been...
You got that?
Yes, just this very morning actually,
nice.
because Dugan has been checking some conjecture that we had on the three-dimensional version of the magic star,
nice.
which actually was named by Mike by some strange Hebrew name, Merkaba.
Merkaba.
Yes, because as a cubo-octaedron structure.
But then you have 8 and 1 in the center, so that's 9. So that's a different number.
Yes, I mean it's something that is a three-dimensional construction.
That's also the star David. You can two.
17 points. Some of them are inside.
Oh, right, if you project it. But what I was going to say is one thing that has a natural 7 is the 3-simplex. So if you take the points that are non-arbitrary, which are face centers, edge centers, and vertices, and you run those to their opposite side. So you take a vertex, run it to the opposite face center, which intersects the centroid. Then you do the same with the other 4, that's 4. And then you do the same with the edge centers, which are non-arbitrary points. Run that through the opposite edge center, which intersects the centroid point. So you've got these 7 axes of symmetry that are fundamental. So it's kind of a fundamental 7 that you have here, and a fundamental
that's
7.
A tetrahedron, and then if you reverse it, right, and then you get the cuboctahedron. If you have a point down, point up.
Right. Yeah,
that's what they got, the cuboctahedron.
The cuboctahedron. Yeah, that's a more straightforward one.
We're rendering the graphics today, so is Fong and Dugan.
Yeah.
And Dugan has the shape right now.
Right. Yeah, so essentially it's something which, when reduced to 2 dimensions, gives this picture. But in 3 dimension, of course, all of these roots which you see as points here, of course, gets. You
don't get Jordan algebras, that's the point.
Yes, of course.
The magic star is related to Jordan algebra, actually to Jordan pairs, and that was the reason why I wanted to study this picture.
Yes.
Okay. Yes.
If you go to 3 dimensions, to lose that.
Yeah, because in 3 dimension, what happens is that the overall symmetry, the manifest covariance of the problem is much smaller than the one that we have here, that essentially is given by the center, which is G naught with a certain index n. And in the 3 dimensions, the maximal covariance is a proper subalgebra of this. So it's smaller, and of course you don't get the whole Jordan pairs, but you got pieces of that. That's what happens. But still, I mean, it's work in progress, but this morning I think we made good progress thanks to Dugan. Okay, so let me come back to this. And so what happens is that any Jordan algebra, any exceptional Lie algebras Ln, where n is a certain index which spans all the exceptional Lie algebras, essentially is this one, 8, 4, 2, 1, and also other classical cases which are in this line, can be decomposed in such a way to have in the center there is essentially the reduced structure symmetry of a certain Jordan algebra of degree 3, which is this one. And then you've got an external A2, which is essentially the one on which you are projecting. Imagine that you consider E8, just to fix the ideas. Imagine that you have E8, you have an 8-dimensional root lattice. And then what happens is that you identify an A2, which is of rank 2. So the two cartons span a 2-dimensional space. You project the E8 root lattice on this 2-dimensional plane or space, and then what you get is this picture. And in the center, in this case, you will have E6, which is the reduced structure symmetry of the exceptional Jordan algebra, which is an Hermitian 3x3 matrix algebras with octonionic entries. And this star-shaped structure on the tips of which we have these exceptional Jordan algebras, and essentially is not only this, but the fact that these are fitting the trees, some fundamental representation of the external A2, so you get essentially two triplets of exceptional Jordan algebras, and as Piero was pointing out, is more even than this, because the antipodal Jordan algebras with respect to the center are making another algebraic structure, which is essentially more fundamental than, if you want, Jordan algebras, and I will say even more than Lie algebras in a sense, which is Jordan pair structure. And Piero, I mean, was inspired to do this back in the 12 because he's an expert in Jordan pairs. And okay, of course, everything can be treated at the complex, on a complex ground field, as mathematicians do, but of course, then for physics, the real forms, and in particular the non-compact real forms, can be considered. So, for example, back in the 2014, I studied this embedding and this magic star structure in applications to gravity models, in particular to supergravity models in 5 dimensions. And I related also to other embeddings which are present in gravity models. Okay, so this is a unifying structure. Let me, for the moment, consider E8, which is the largest finite-dimensional exceptional Lie algebra. And as you see, E8, so the fundamental representation, which is identical for E8 to the adjoint representation, because E8 is essentially defined as acting on itself. And so you see that decomposes as an A2. For the moment, forget about the C upper script, which has a physical, actually, interpretation, but let's put it aside for the moment, plus a triplet of exceptional Jordan algebras, an anti-triplet of a conjugate set of exceptional Lie algebras, plus, of course, the reduced derivations of the Jordan pair, which you can show to be the same, to be isomorphic to the reduced structure of the single Jordan algebra, making the pair. Well, in turn, what happens? This is the magic of E8, if you want. And this is only for E8. The derivation, the reduced derivation of the Jordan pair made out of the exceptional Jordan algebras is itself an exceptional Lie algebras, so enjoys itself a magic star decomposition, because this is nothing but E6. In particular, I mean, I'm not considering real forms, so it's E6. So E6 itself has a magic star structure, so once again can be written as an A2, of course another A2 with respect to this. And in this case, you still have a triplet and anti-triplet, but of a smaller 3x3 Jordan algebra, which is defined actually not with octonionic entries, but with complex ones. And of course, still in the center of the E6 magic star structure, you will have a reduced derivation of a Jordan pair, this time made with a complex rank 3 Jordan algebras. And
sorry, Alessio, in the center of the magic
in the
star
center of the
E6,
center,
it is A2 plus A2.
Yes,
But
this one.
okay.
Of course.
Okay.
I just made it explicit in the next line.
Perfect.
Yes. So you see what E8 it's all about. E8 is about 4 commuting A2s plus essentially two sets of triplets and anti-triplets. One on the exceptional algebra, on the exceptional Jordan algebra, and one on the complex Jordan algebra. They have the same structure, this one and this one, but this one is Hermitian with octonionic entries, and this one is complex, is Hermitian with complex entries. So you see that this is a very, if you want, decomposed interpretation of E8, which which exploits two magic star decompositions, one after the other. And there is essentially an interpretation of all these in terms of symmetries of what? Symmetries of Jordan algebras. Because, for example, E8 can be regarded as a certain symmetry which goes under the name of quasi-conformal symmetry. This is something which was discovered quite recently as a quasi-conformal realization. So if you go on the relevant non-compact real forms, you get these expressions. And so at the end of the day, you can essentially relate this to a quasi-conformal symmetry of exceptional Jordan algebra. And for example, the E6, which gets further decomposed, as I write here, is nothing but essentially reduced structure symmetry of exceptional algebras. So this is just an example on how the magic star decomposition works, in particular in this example, which stands on its own for the fact that E6 itself is an exceptional algebra. And so it turned out that then magic star is not only a unifying tool, so it's not only formal and elegant, but it's very effective in order to do computations and in order to characterize even visually some other algebraic structures which arise from Jordan algebras and Jordan pairs. And for example, let's come back at the case of the E8 magic star, when you fix this parameter that now here is a new parameter, n equal 8, but this can as well be an E6 magic star if you fix the parameter new to 2. But what it's important, let's fix it to 8 for the moment, so let's consider the E8 magic star. So what happens is that, remember in the center one has E6, and it turns out that if you consider the set of roots given, by this shaded line, what happens is that this is E7. Because E7 has a 3-graded structure whose center, whose 0-graded part is nothing but this. So essentially E7 is given by E6 plus exceptional Jordan algebra plus the conjugate 1, and then there is of course a Cartan, which is essentially given by an orthogonal axis to this plane, to the plane of the screen itself, which remember is the plane defined by the two Cartans of A2, which defines the magic star projection. And there are also other structures. For example, the so-called Freudenthal triple system, which from the point of view of the vector spaces is just a Jordan algebra, a cubic one, plus its conjugate, plus two one-dimensional vector spaces, which in this case can be taken to be some roots of A2. And it's very nice because when I met Piero, essentially I was coming from supergravity and essentially Maxwell-Einstein gravities, and these Freudenthal triple systems are very important because essentially they parameterize the charges of black holes, and so they play a prominent role because the invariants of these algebraic systems are nothing but the entropies of black holes. So and it was very interesting to see them in this very elegant approach based on the magic star. And then there is even, one can consider a pair of those. So you see a pair of Freudenthal triple systems, which then appear to be studied quite recently, actually, by these mathematicians, because, of course, they can be defined in an axiomatic way, so essentially without relying on any explicit realization. So this is just to say that the magic stars, it's a tool also to visualize other algebraic structures and also the relations among them in a very efficient way. Yes?
So I like what you're saying about all of the rich decomposition inside of it. And I like to think sort of about the E series as your richest algebra and your richest geometric point space. So I like to think of, for example, A6 and D6 as subalgebras and sub-point sets of E6. But to me, the one that's the most intriguing is the identity of E8 as the union of 3 copies of A8, because I'm thinking, I keep thinking about this crazy thought Mike had about 3 directions of time and how that might relate to this notion of the degrees of freedom of a shift vector code for the random walk of the shift vector in E8 that animates the Elsner-Sloan quasi-crystalline 4D, which then animates the QSN.
Okay, yes. I think when you say that there are more than one, if I understand well, A8.
The union of 3 copies of
yes,
A8.
I think we had also some discussion on this by mail, also with somebody else. Yeah, the point is, this is correct. I would like to stress that these 3 copies of A8 inside E8 are not, of course, commuting. No, I mean they are not disjoint sets of roots. Of course,
only one is root set. The other are weight sets.
Yes, absolutely agreed. Because what I know from the theory of Lie algebras, there is a unique root system of A8 inside E8. But this is consistent with what you are claiming. I mean, of course, then you can realize essentially E8 by slightly moving, if you want, this root system, of course, in a way that doesn't form any other disjoint root system, but of course you are spanning in this way the whole set of roots of E8. So this essentially, it's another way of seeing E8. You see, either you see it as a union, as you say, of 3 copies of A8, or you can see it, for example, through the magic star as very simply as 4 disjoint copies in this case, of A2, plus the 2 set of triplets. So these are all equivalent and they of course speak each other. What you mentioned about the multi-time stuff, of course it's in some sense it's more natural from another point of view, and it's an embedding that I will actually be mentioning in the next slide. So let me comment later about this. So I presented the magic star, and but now we are considering something else. Let's look at the tips of the magic star. You know that at the tips of the magic star there are these matrix algebras, 3 by 3 matrix algebras, which are called Jordan algebras. In particular, in the case of E8, we have the exceptional Jordan algebra. And I would like to stress that there is this very interesting maximal embedding between Jordan algebras, which is telling you that inside any 3 by 3 Hermitian matrix over a division algebra, maximally embedded, there is another cubic Jordan algebra, which is no more simple but rather semi-simple, which is essentially given by the same kind of Jordan algebra but of a smaller rank, of rank 2, in direct sum with the reals, of course, because here I'm working with the reals, but I could also put a one-dimensional ground field like the complex one. And what happens is that essentially one starts with the expression of J3n, so a certain element of a cubic Jordan algebra, and sets to 0 these components. So essentially, if you want to isolate the 2 by 2, the formally 2 by 2 part, upper part, sets to 0 these two elements, which belongs to the division algebra you are considering, and then still has these real degrees of freedom. And then essentially you see that this is nothing but J2n by the very same definition that we use for J3n. And then there is a real lower right component. And this is an element of this cubic semisimple. This is the unique semisimple rank 3 Jordan algebra. These were classified a long time ago by Jordan, von Neumann, and Wigner. And why I'm telling you this? Well, because if we study the symmetries related to this maximal Jordan algebraic embedding, we found something really surprising, even for physical applications. And this is the relevant fact. Essentially, we have as symmetries, which goes under the name of derivation, reduced structure symmetry, conformal symmetry, and quasi-conformal symmetry. All the exceptional algebras but G2. For the moment, G2 I will not be considering, even for the reason that doesn't enjoy an exceptional periodization. So for the moment, let's put it aside. I may comment on it later if you're interested. But on the other side, so if we consider the symmetries of this side of the embedding, we always obtain some orthogonal algebra, or pseudo-orthogonal, I would say, in these other cases. And what happens is that if I decompose the symmetry of this set of Jordan algebras into the symmetries of this other set of Jordan algebra maximally embedded in that, what in general I find is that the roots, or if you want, the generators at an algebraic level of each of these exceptional Lie algebras are decomposed as the roots or generators of a pseudo-orthogonal Lie algebra plus a spinor representation. So you see, for example, let's take F4. F4 is the derivation of J3 8 when we put n equal 8. So are the derivations of the exceptional Jordan algebra. This decomposes as S on 9 plus S16, where S on 9 is the derivation of R plus J2 8. And so you see that in some sense you have bosons which can be associated to the adjoint representation of S on 9 plus some fermions which can be associated to spinors to the 16 of S on 9. And essentially you've got the same in all other exceptional Lie algebras. You see that you get a certain part which is a pseudo-orthogonal Lie algebra plus some spinors. In this case, for example, Majorana-Weil spinors, 16 and 16 bar. For in the case of E7, there is a pair of 32s because essentially you've got this non-compact form of D6 plus this split form of A1. But you see, the moral of the story is that why this essentially leads to another interpretation of the adjective exceptional for what concerns Lie algebras. Why are these exceptionals? Because by virtue of this maximal Jordan algebraic embedding, translated at the level of the symmetries of the Jordan algebras, which are Lie algebras, any exceptional Lie algebra, this actually can be shown, is quite trivial also for G2, but any exceptional Lie algebra contains within itself a set of bosons and a set of fermions. This never happens for the classical Lie algebras. If you decompose a classical Lie algebra with respect to any of its maximal Lie subalgebra, you will never get the adjoint of the maximal subalgebra plus the spinors of it. Instead, this always happens with this kind of embedding. And this is something that I think is very interesting for physicists.
Simple, of course.
Yeah, sorry, simple, of course, because one can think about more complicated things, which are non-simple, non-semi-simple, or even non-reductive. Lie algebras, in that case, you can do, this statement that I just did is violated. I'm talking about simple Lie algebras, which I think we all know and love and are very nice and at least are the first choice in order to make unified theories of bosons and fermions. Okay, so essentially exceptional Lie algebras have, I would say, an inner supersymmetry in the sense that unify bosons and fermions in their very adjoint representation. So essentially one can split in a very mathematically rigorous way all the generators of exceptional Lie algebras in bosonic and fermionic ones. So this is something which I will call another kind of supersymmetry, of course not in the sense of space-time supersymmetry as I would call. Even though these are some relation to superalgebras, Z2 graded algebras, filtered algebras, and so on. But I mean, for the moment, we are just talking about simple Lie algebras, and this makes the exceptional Lie algebras stand on their own. Okay. Okay. So far, I just talked about a way to unify and to look in a different perspective all exceptional finite-dimensional Lie algebras. But the story, it's more complicated, and even though I think it's very nice and has a lot of surprises, because Mike, back in the, I think in the 2 years ago, when we were meeting in San Francisco, said, okay, but is there a way to be inspired by the magic star and keep going? I mean, we've got this star-shaped, let me just come back to the, let me come back to the first page and to the magic star structure of, So essentially, 2 years ago, more or less, we had this structure, and we had very precise numbers which were essentially telling us the dimension of the vector spaces. So the set of roots that we had here, that we were very happy because these were not only vector spaces, but we might endow these vector spaces with an algebraic structure and might recognize some very interesting algebraic structures. But of course, we were constrained and bound to have those dimensions. Then Mike started putting numbers, and we were very, I would say, skeptical about, so what are these numbers? I mean, they don't make any sense. They are not fitting in E8 because we cannot go beyond E8, keeping the finite dimensionality. And so because E8 is the largest finite dimensional exceptional Lie algebra. But then what happened is that it turned out that this magic star structure could be generalized, and could be generalized in a way that actually we would have never essentially thought about, because this goes beyond Lie algebras, but goes beyond Lie algebras in a very controlled way, in a very, if I will say, mild way. And once again, this generalization starts by looking at those embeddings that I just showed. So at those embeddings in which any of F4, E6, E7, and also E8, I will present in the next slide, algebra can be written as an orthogonal or pseudo-orthogonal Lie algebra with some factors plus a set of spinors. And we said, okay, we can keep going with this because essentially we know that the spinors enjoy a Bott periodicity. In general, I mean, Clifford algebras, and they are fundamental representations and so on. They enjoy a Bott periodicity also for what concerns reality properties and conjugation properties. And so essentially we just wrote down these generalizations where essentially for n big n capital equals 0, we come back to the previous exceptional Lie algebras.
So Tony Smith says that he practices Clifford algebra in a particularly different geometric way. And then Richard's old mentor, David Hestons, is sort of like considered the modern father of geometric algebra. But honestly, I don't fully understand the nuanced difference between Clifford algebra, which I see as a vector algebra, versus anybody's geometric form of an algebra. But without going into any distracting discourse on that, all of this can be viewed all geometrically in our way of thinking as E8 as the lattice version of the algebra, the projectors as transformers, correct?
Yes, because essentially, I will tell you later, and also Piero will be elaborating more later. Essentially, we have a root, we have a generalized lattice constructions of this. So we have a geometric way to construct these algebras. Of course, the important point that I would like to stress that these are no more Lie algebras, but the violation essentially of the Jacobi identity for these new algebras is confined to a very precise subsector, and the subsector is essentially given by these spinor extensions. So we have a way to control the way in which these algebras, which can be constructed in a very precise and geometric way, violate the Jacobi identity. And then, as Piero probably will be pointing out much better than me later, the violation of the Jacobi identity is not a bad thing if you want to essentially stay, and you have many justifications and reasons for this, in a discrete setup. So essentially these algebras never, if you want, go to the group level. So we never exponentiate this, because for an exponentiation you need to have an associative structure, and of course Jacobi should hold. So essentially, but we don't need that, because we have a way to construct those by a lattice, and there is no reason to go to a continuous structure. And then probably Piero will be mentioning about the physical meaning of this later. And so on. So these are very well defined, even in a geometric way, algebras, and one can compute the commutators. So we have a way to compute the commutators in a very simple way through a function that essentially is due to Victor Katz, which is called asymmetry function. And there is a notion of roots for these generalized, if you want, algebras, which goes under the name of magic star algebras, which is generalized roots. So at the end, we don't get a root lattice. We get a generalized root lattice. And the generalization is very well defined. I mean, we have a rigorous definition of this generalization. So essentially, the ingredients of this are both periodicity for what concerns essentially the spinor extension, and let me anticipate that these are non-reductive Lie algebras. So these are not Lie algebras. They will seem like non-reductive Lie algebras, but they are not, because essentially this spinor extension is not trivial. These are not abelian is not a bunch of abelian generators, but they have a very non-trivial commutator structure, and this makes these algebras interesting. Otherwise, we will just find a bunch of non-reductive Lie algebras that were already known. Of course, let me stress that when the n capital parameter is set to 0, we of course get back to the exceptional Lie algebras that I've been considering before. Okay, so the key result that actually made all these strange numbers that Mike started writing back 2 years ago on the whiteboard in San Francisco is that when you take this generalized root lattice and you project always on a two-dimensional plane, which is still identified by the two cartan of an A2 subalgebra, you still get this picture, even for n capital equal 1 or even higher, any natural n capital parameter. And this is amazing because a priori there was no reason for this dislocation and arrangement of roots. But even more surprising, on the tips of the star, what do we have? Because we know that we cannot go beyond exceptional Jordan algebra. Because, I mean, you cannot define essentially Jordan algebras beyond J3O, so beyond the Hermitian matrices over the octonions. Well, surprisingly, we found out, after many struggles, that on the tips of this generalized magic star, there is the very structure that was introduced by Vinberg, which generalized Jordan algebras, staying always as a 3x3 matrix. So these are 3x3 matrix algebras. And you might think, okay, but how can I construct a 3x3 matrix algebra which is Hermitian? I already exhausted all the list of division algebras I can construct them on, because reals, complex, octonions, quaternions and octonions. I have nothing more, because I could go to sedenions or even stranger things, but these are no more division. And the division is needed in order to make the matrix algebra well defined in this case. Well, the point is that there is another structure that I will present later, which goes under the name of T-algebra. And essentially, this very structure is what we found on the tips. So what we found to be made by the roots of the generalized root lattice projected in these points on this plane.
Is it this may be a silly question, but in some sense, is this super-algebraic structure represented by these algebraic relationships of matrix algebras in this magic star structure, is it in some sense like a tensor network?
Like a tensor network?
Insofar as a tensor network might be thought of as a sort of super network of separate matrix
sites. He's just asking the question of considering the T-algebras, right, as some tensor structure, right? You have...
This should be tensor, not matrices.
Yeah, so these would be...
has just two connections, it's not interesting.
This would be like a generalized tensor network.
But we have these 3x3 matrices.
Yeah, we'd have T-algebras instead, yeah.
On the tips of this star, we have these 3x3 matrices. Let me just presenting them. So you see, just to answer your question, maybe, I don't know. So you see that still you have real numbers on the diagonal. You've got a vector space which is actually a vector of some orthogonal Lie algebra. And then you've got spinors, here and here. So this is, you may see, I mean, like a bunch of vector spaces inserted in this formal 3x3 matrix. And why they generalize the Jordan algebras? Well, because in the Jordan algebra you still have this thing, but as I will show you later, you have triality. Here triality is broken. Why is broken? Because the dimension of these vector spaces, which are representation spaces, spinoria representation spaces, is when n capital is different from 0, is very much different from the dimension of this vector space. You reduce to Jordan algebra when you put the n capital parameter to 0. Because in that case, there is a triality relating these three representation spaces because they have all three the same dimension. So I don't know if this answers your question, but maybe yes, maybe not. I'm not an expert in tensor networks, but this is, you might say, okay, but this is a way to generalize Jordan algebra. Maybe it's not unique. But instead, Vinberg proved that in order to have a well-defined matrix algebra, you must have this structure, and you must have that these vector spaces are vector and spinor representation spaces of a certain orthogonal Lie algebra. There are no other representation theoretic structure that will appear in any generalization of Jordan algebras. So this is the most general one. And we were very pleased to find them on the tips of this generalized magic algebra. Magic star structure, if you want, which is related to this generalized magic star algebras. So,
can I make a question?
Yes,
in
of
the
course.
previous slide?
The previous slide, yes. This one?
Yeah. In the beginning, you said that you decompose E8 in 4 copies of this.
Yes.
And
well,
now you are saying that you can extend this to infinity. So this is the
very good question.
And this is the adjoint and the fundamental representation of SU3. So this is like the building block.
If I understand your question well, let me come back to this way of seeing E8. But the answer to your question is positive. I mean, it's affirmative. Let me see. Yeah, this one. So before I just said that E8 is nothing a bunch of commuting A2s, 4 commuting A2s, plus these triplets of exceptional Jordan algebra and the Jordan algebra over the complex. Okay. So by virtue of this exceptional periodization, essentially one can do the same in the sense one may consider the nth generalization of E8, and once again what happens is that you will still have this A2, and in turn E6n, which will be in the center, let me just, E6n, now this is the original magic star, but imagine that now you have the exceptionally periodized one. In the center of E8 nth generalization, you would have E6 nth. And then once again, E6 would enjoy the same exceptional periodization with a magic star structure. And so what happens is that still you would have an A2 inside this E6n. And now the point is that these further A2s will be more complicated to be defined as far as this I will never consider, but I think that it can be done. But I think I'm even with Piero that agrees with me. I will say that still E8n is given by 4 commuting A2s. What changes? It changes this. I mean, these 3x3 matrix algebras are no more Jordan, are of T-type, are Vinberg's T-algebras. And essentially, the fact that this is no more a Lie algebra resides in the fact at this level, and this is very interesting because I would say that resides in the fact that these entries in the case of E8n, where n is different from 0, are no more triality symmetric. So these are still matrix algebras, but there is no more triality. So this is a way to see how the breaking of Jacobi in these exceptionally periodized exceptional Lie algebras is related to the breaking of triality in the 3x3 matrix algebras appearing in this decomposition. This is very interesting. And essentially this is, so it's a very good question. I mean, it's a way to break in again E8n, which is the largest of these exceptionally periodized exceptional Lie algebras, breaking into smaller pieces which are still parameterized by the quantum numbers related to these 4 A2s.
Yes. So would E8-1, would that would have like E6-1 in the middle, and then E6-1 would have E8 in the middle probably.
Sorry, so E8 would have E6 in the middle with an A2 in the external structure. Then E6 itself has an A2 again in the external, and in the center A2 plus A2.
Right. And then, so now let's go up to the next level of EP, right?
Yes. But you still have those 4 A2s. So what's changing is just the dimension. This is a very interesting thing. I mean, what changes, sorry, I'm going forward, I should go backward. So what happens is that when you go to the next level in DP, what changes is just the dimension of those 3x3 matrix algebras, because they become larger and larger, because if you see the total dimension of a cubic T-algebra, which actually is of special type, because there is also a classification of these T-algebras, you see is growing with n. So essentially when you go to the next n, of course this grows linearly, but this grows with a power. Right. So you see that the spinors become larger and larger than the vectors, and so if you want, triality is more and more broken into a duality of the Majorana-Weil spinors against a much smaller vector. But that's the only thing that changes.
Let me just ask this question then. So could you have more than 4 A2s at higher levels of EP?
No.
Or would it stop
No.
at 4?
You are stuck with 4 commuting A2s. That's the point. And this is in some sense the beauty also of it, because it keeps being very simple at the level of the structure. You've got 4 commuting A2s. And so this is very nice to me. And the way that you relate the violation of Jacobi to the violation of triality in the T-algebras on the tips of the magic star is something that I never considered before, so it's quite interesting. Okay, so let me go, let me skip something. So this is just to tell you that when you have Jordan algebras, you have triality, and I was elaborating on this, and when you have T-algebras, you don't. But there is, I mean, in some sense, this is the price that you have to pay when you go beyond the 8. Okay, so let's talk about invariants, because invariants in physics, I mean, are very important, because whenever there is an invariant under a symmetry, this has a physical meaning. And so one might well study the invariant structures of these T-algebras that appear in the on the tips of the exceptionally generalized magic star. And I was knowledgeable of the invariants of the Jordan algebras, of cubic Jordan algebra. Why? Why I knew them? Because they appear in supergravity and essentially in Maxwell-Einstein gravity. So whenever you have a bunch of Maxwell fields coupled to gravity, and possibly with a nonlinear sigma model of scalars, you may relate these to certain Jordan algebras when you have further symmetries. And the invariant of the Jordan algebra, essentially the norm, or if you want, the formal determinant of this 3x3 matrix, essentially was related to the entropy of the black hole solutions in these Maxwell-Einstein systems. It turns out that for the T-algebras, you still can write down a unique cubic invariant, is a cubic polynomial, which is the so-called norm of the T-algebra, or which is also formally the determinant of this. And there are many connections to the Maxwell-Einstein supergravities, which I will not talk about that, but it's very interesting that you can, by this unique structure, and the uniqueness is a non-trivial mathematical result, which is still unpublished actually, but essentially it can be done, can be derived. Through this norm, you can define a concept of rank of elements of the T-algebra. Essentially, you will say that an element is maximal rank when the norm of this element, so the formal determinant of any 3x3 such element, is different from 0. Then will be rank 2 when this determinant is 0, and then will be rank 1 when not only this is 0, but even the first derivative and as a vector is 0. This is an invariant definition of rank for elements of a T-algebra, and as I told you, this can be transposed in Maxwell-Einstein systems which enjoy some symmetry, in which the entropy of the black hole is nothing but pi times the square root of the absolute value of this invariant. And there are some mathematical investigation in this, because essentially Vinberg introduced these T-algebras, but after him very few mathematicians studied these algebras. So there is still many things to be determined, I mean, to be investigated, and we are trying to do that. Okay, so how much time do I have left, or can I go home forever? Let me I think you have abounded the patience. So I mean, this I will skip because essentially is I told it in words. Let me make an example just to be very funny, which is this one.
So I just would like
yes.
to return to the Wittgenstein entropy.
Yes. You want me to come back to the entropy? Okay, good. So let's come back to the entropy, which is, where is it? Sorry, I always keep going forward, but I should be backward. Okay. Here it is.
So square root of n over q, what n means here?
This n calligraphic?
Yeah.
This n calligraphic is, if you want, the determinant of the 3x3 matrix. So it's an invariant under some symmetry.
So
as this expression, if you want, as this expression where this v and psi and r are, if you want, are these ones. R3, V, and psi are related to these vector and spinor spaces, subspaces of the T-algebra.
How this is related to the actual physical area of the black hole?
To the physical?
How is it related?
The surface area of the black hole. Because
Okay.
here is quite related to the internal space, not to the...
Well, allora, right. So I'm talking about the Bekenstein-Hawking entropy. So essentially, this is the leading, the macroscopic, or if you want, a leading order contribution to the entropy. And this is essentially 1/4 of the area of the event horizon, of the extremal black hole. I'm talking about extremal black holes. I didn't specify, but I mean, a particular class of black holes have this entropy, the extremal ones. So in the extremal ones, what you know is that the Bekenstein-Hawking entropy area formula is telling you that the entropy may be related to a geometric quantity which is 1/4 of the area of the horizon in certain units, and essentially this is SBH over pi. So 1/4 of the area of the horizon in certain units is just the square root of this. And these Q are the charges which you can associate to the background of the black hole. So these are charges which are conserved because you have some gauge symmetries around. So you have some symmetries of the set of Maxwell fields which are coupled to this background. So you have a certain symmetry which is called electromagnetic duality, which is mixing linearly the Q's, but what happens is that this is invariant. It's an invariant polynomial under the action of this electromagnetic duality. So, but this must be actually because the entropy is always invariant under the electromagnetic reparametrizations that you have under this symmetry. Okay, so it's a particular class of black holes, and I'm considering the leading contribution to the entropy. Of course, you might have sub-leading contributions. And then that's another problem because one should study which other invariants enter the game. I just told you that this is unique, so should not enter, but these sub-leading contributions enter the game when you have quantized charges. So essentially when the entries of your T-algebra are no more continuous, like the one that I will have here, because I mean these are real numbers at the end, but will be quantized, so integer or some more fancy discrete ground fields like Adels, Icosians, or whatever.
But here you are specifying that NQ equal to 0 for rank 2? Or
for rank 2? No, this is rank 3.
Yeah, it's
when you
only
put
values for rank 3, right?
For rank 3. Sorry, good question. I mean, of course, when you have rank 2 or rank 1 elements of the T-algebra, the entropy, the leading order entropy is 0.
Which means that there is no black holes.
It means that at the two derivative description of gravity, so at the Einstein level, this will be a naked singularity. Of course, the way out to this is to say that the black holes, which are supported by charges which belongs to the rank 2 and rank 1 orbits of the T-algebra, cannot be described by Einstein gravity, but some discretized or even in the effective way of approaching things by some higher derivatives. So I mean, it's an equivalent essentially way of saying. This means that these black holes are intrinsically quantum, the ones supported by rank 2 and rank 1 charges. If you go to rank 3, they may have a well-behaved classical description with this as a leading order entropy.
And do we have observed such black holes?
Well, that's a big question. I mean, you know that we are very happy that we observed some black holes dancing together and then melting, and I mean gravitational waves. I would say that there are some astronomical black holes, astrophysical black holes, which are very near the extremality regime. So I would say that to me, extremal black holes are much less unrealistic than most of people think, because I mean there are many astrophysical black holes which are very near the extremality bound, which means that within certain regime can be approximated by extremal black holes of this kind. Of course, we never observed exactly extremal black holes because, of course, it's a very...
But my question was more precisely about the one of rank 2 or rank 1.
Ah, okay. I mean, you know, that's I'm not the right guy to ask this because you should experimentally measure charges of a black hole. These are electric charges and magnetic charges. So, I mean, most of astrophysical black holes are neutral. So every black hole is neutral at the, because from a distance, all the electric and magnetic charges, which I mean don't even, were not even observed, the magnetic charges, but I mean all electric charges will be screened. So I mean it's a problem of measuring things with black holes. But at least we know that black holes exist, and some of them can be quite neatly characterized in the extremal way.
There's been suggestions that extremal black holes can be characterized as elementary particles in some settings.
Yes, because the characterization of the elementary particles will pertain to me to the smallest rank black holes. Because why? Because there are some mathematical ways and also, I mean, some physical intuition that the well-behaved large, the so-called large black holes, which have a non-vanishing Bekenstein-Hawking entropy, will be made by building blocks which are made by rank 1 things. And of course, the string theory has been playing around with this, because these are what in string theory are characterized by bound states of D0 branes, which are in some sense the building blocks of which all these gravitational objects are made. So, okay, so I hope I answered a little bit to you.
But I think for rank 1, you might have also a minimum or maximum value of NQ, because here you don't...
No, NQ, no, for rank 1...
NQ could have a value.
No, because I mean, since n is homogeneous, if this implies this, of course. So I mean, for rank 1 you have NQ 0, and more than this you have this, because this implies this, but not the other way around, of course. Yeah. So n is 0 for rank 2 and rank 1. So these are the so-called small black holes.
Alessio,
Okay.
you think you can finish in 20 minutes?
In 1 minute?
20.
I can finish in 20 minutes, thanks. Okay, thanks for, all right. Yes, definitely. So, triality breaking in T-algebras. Let me come back to these T-algebras. Essentially, what Vinberg will say, Vinberg is still alive. I mean, it's in Russia, it's more than 80, but it's still going strong and working. And Vinberg essentially introduced and classified these 3x3 algebras, actually by this n by n, but we are considering the 3x3 cases. And essentially, our T-algebras, our in the sense that we found them on the tips of the exceptionally periodized magic algebra, are of the special type, which means that you have two sets of spinors of the same dimension, and then you've got another vector space which is made by some other representation, not a spinor. So the dimension is the same for these two entries, but not for this. And this is how triality is broken. And of course, it's recovered only when n is equal 0, but then you get a Jordan algebra. You get an exceptional Jordan algebra in the case in which you are constructing over the octonions. But then there is a strange observation that was actually pointed to us by Eric Weinstein back in 2016 when we met together in San Francisco. He said, okay, let's consider 24 dimensions. And if you compute the vector representation of SO24, which is D12, and also the spinor, the chiral spinor representation, you get essentially 24, which is the 24-dimensional vector, nothing surprising. And then you get a 2048 dimensional chiral spinor, and of course the conjugate, because there is chirality in even dimension. Of course, if you only have this, there is a huge breaking of triality. You see, it's 24 against 2048. But then what happens is that the difference between the dimension of the chiral spinor and the vector is itself the dimension of an irreducible representation of SO24, which happens to be in this case the 3 form, so rank 3 antisymmetric tensor. And this we put forward the conjecture that essentially there might be some weaker version of triality at work in some particular, if you want, point of the exceptional periodicity. So exceptional periodicity will be characterized, this is still a conjecture, the first example will be this. We never investigated that in depth, but we should try more. There will be some particular points along exceptional periodicity in which not triality is restored, but some weaker version of triality. For example, here, what will mean weaker version? You still have your chiral spinor, you still have your vector. The difference between the dimension of these vector spaces should still pertain to the dimension of some irreducible representation of SO24. And the first example, still mysterious, is the thing in 24 dimension. This is just a curiosity that I wanted to share with you, if you have some insights.
So that's the 1 form and the 3 form.
Yeah, sure. It's the vector and the 3 form of SO24. That's it. Okay, so I already anticipated that EP algebras, so E8n, E7n, E6n, F4n, as I defined before in the previous slides, are not Lie algebras. Indeed, you can show that Jacobi is violated, and is violated not in the orthogonal part, in the pseudo-orthogonal part, but in the spinor extension. So if you consider the generators associated to the roots pertaining to the spinors, if you fix one generator, you will always find other 2 generators such that Jacobi is violated. So these are not Lie algebras. Jacobi is failing in the spinor sector. And in order to show this, it's crucial that these spinors are not just abelian generators which you just add to the pseudo-orthogonal reductive part, but are non-abelian generators which have a well-defined commutation relations which are computed with the asymmetry function. This was an important tool to compute in a very simple and precise way all the commutators in these EP algebras. As I said, in some sense, this violation of Jacobi is the price that we have to pay in order to go beyond the 8, keeping the finite dimensionality. Because you should know that in mathematics, there is a precise way to go beyond the 8. But this implies that you go to infinite dimensional Lie algebras, which means have an infinite dimensional number of generators. And this is pertaining to the so-called affine extension, Katz-Moody, and generalized Katz-Moody extensions. You keep adding nodes to the Dinkin diagram. We can also do this trick with the Dinkin diagram, because there is, as Piero will be pointing out at the start of his first talk, there is a way to construct the EP algebras by adding special nodes to the Dinkin diagrams of orthogonal Lie algebras. But the way is very different from the Katz-Moody way, which keeps the Lie nature but goes infinite dimensional. So goes immediate E9, which is E8 plus, is already infinite dimensional. Instead, with the EP algebras at each n capital, which is the parameter of the generalization, we keep the dimensionality fixed and finite. And we have a certain sector of the algebra, so a certain subset of generators which violate Jacobi. And as Piero will be pointing out, for physical applications, this means that we never can use these EP algebras for continuous symmetries. But the good news is that in our model and project proposal, there is no need for continuous symmetry, because the space itself is discrete and does not exist without the interactions. Since interactions are discrete, so space is. And time is just a clock of interactions. So, okay, this is something that I would like to anticipate. So it's not, for us, it's not very worrying to have a non-Lie algebra, in particular to have a non-Lie algebra in which we can control how Jacobi is violated, and we know where it is violated and how, because we are aiming at a discrete space and discrete time, and there is no way to exponentiate and go to the group structure, as for the usual Lie symmetries in physics. Okay? Of course, we are working in to get a mathematically rigorous description of these algebras. These are, if you see the original paper, and as maybe you can guess from here, these are very simple Lie algebras. These are explicitly constructed in a geometric way from generalized root lattice. They have very simple commutators. Essentially, the commutators are either 0, either 1, or -1. So essentially, in a certain Chevalier basis for these algebras. So these are very simple, but we didn't find yet any characterization of this axiomatic structure in mathematics. So we are trying to do our way, to find our way to axiomatize. Essentially, we are working with some mathematicians to essentially define a kind of weaker Jacobi identity, which would hold also for these EP algebras. But I mean, still work in progress.
So there's a sense in which there's an inherent ternary logic to these, because you just mentioned the 0, 1, and -1 commutative values.
Yes, yes,
So
yes.
there's a certain ternary.
It's a kind of Q-trits,
Yes.
right? So I mean, yeah, we might go with this, because there is essentially a quantum information interpretation.
Computational perspective,
Yes,
that would be helpful.
from the computational perspective, there is a Q-trit interpretation of all this. Okay. So let me see what I can add. I mean, there are many things to be said, but I would like just to stick to the important points, just to leave you with some ideas and fundamental concepts. So I will just finish with some points. So what we are working about now. So as I said, concerning Vinberg algebra, there is still to do almost everything, because the symmetries of the T-algebras have never been studied. There is very limited literature on this. And of course, this is important because whatever physical system you are describing with this, the invariance of the T-algebras, for example, we showed that the invariant of a single T-algebra is always unique, and is given by that norm that I described with calligraphic. And this is very important. I mean, the uniqueness, there is a unique invariant. But there might be other system of T-algebras which admit, constructed with T-algebras which may admit more than one invariant. So, I mean, we are still working on this. And then there is a way, a geometric way to go beyond the so-called projective spaces based on division algebras. This is something more exotic, which essentially is relying on the fact that we might use these EP algebras to describe isometries of certain spaces. This is very interesting. In some sense, we would like to have a geometric characterization of the exceptionally periodized Cayley-Mouffe plane. But that's, I mean, something that still is under study. Of course, one may ask, okay, but you have this sequence of EP algebras parameterized by a natural number. Can you characterize the n equal infinity limit? Because essentially this would be the final theory, or if you want, the final symmetry of a certain theory. And this is very interesting, and in my opinion has some very nice relations to what Ray has been, well, this is, I mean, see Ray at Shine's talk, because this is a similar talk I've been giving at Prague this summer, and Ray was talking about infinions, which are a certain Cayley-Dickson infinite way to describe some algebras. And so probably is something, this n equal infinity limit of the exceptional periodicity might be related in some cases to infinions, but still this is something very interesting that we are working about. I told you that starting from Jordan algebras I can make more general structure like Freudenthal triple systems, which are a Jordan algebra plus the conjugate plus a singlet, one-dimensional vector spaces. And these are very important because are in some sense bigger, and you have more freedom. These are more general structures. We are studying whether something similar might occur starting from T-algebras. And some mathematicians have been studying similar structure quite recently. And the symmetries of all these algebraic structure to be axiomatized should be essential in order to describe the physical, I mean the physics that we want to do with this. And Piero will be mentioning this later. I will say that I have been working with Piero. It's a great privilege to be Piero Turini's collaborator since 2015, and then Mike joined. We call ourselves a Jazz Fits Trio, and
Alessio plays jazz, by the way.
Okay, well, I used to play
Jazz
actually.
is his name.
And recently also I will say that David is joining us, so it's actually more like a quartet. Recently, I mean, for some collaborations. And we want to do some physics with this. And the physics, as I have been anticipating more than once during the talk, it's starting from a discrete space. Actually, it's starting from interactions. Space does not exist, in our opinion, without any interaction. So it's starting from interaction, and we are concentrating on an E8 model, but nothing prevents us in the future to go beyond E8. And essentially, we think that a final theory of quantum gravity would have much to do with this object, which is it's very mysterious. Okay, so this is a personal opinion. At the very end, the more we try to characterize this, the more we gain insights on some final theory of quantum gravity. So I would thank you for the attention. Thanks.